So you design a system to a set point. In reality, you left here the set point. So what you do is you measure the difference between the two, at least for the feedback controllers. You take a difference between the two, feed it back to the system, change your controlling variable, and so you can basically go back to the target. So that you're learning control. But here we are not doing that. Here we are not able to change C. We don't have it online. Now, that would be a good system. You could say, well, you know what? We tune the scrubber. We design the scrubber in a way that responds to C and takes a control into our, which actually is possible. What you have to do is you have to change the flow rate of sulfuric acid, so you could do that. But that's not what we are doing right now. Right now we are saying that the design is already completed. We have some concentration coming out that could vary because of any of these changes to the system. Does that make more sense? All right. So this is our cost, and this is our most likely cost. So let's calculate what this is. Now, of course, let's put some values for Cmin to Cmax. Now, the probability distribution function, somebody could say, in reality, probability distribution function will likely be. So what we are going to assume is that the probability distribution function is actually all probabilities are equally likely within some range. So we're going to say that we have some Cmin to Cmax, and all probabilities are equally likely. This is not the most likely distribution. We're only assuming that simply because any other distribution, first of all, where are we going to get it from? In reality, it's going to be more like a Gaussian. Okay, centered around C star. But for simplicity, we are going to assume that it is Cmin to Cmax, all of them are equally likely. Okay?
Is that a unit step function? Or
so this is a step function. This is called a Heaviside function. So if this goes from Cmin to Cmax, what should be the value of this probability?
1.
The integral is 1.
1 over.
1 over Cmax, right? 1 over Cmax. Okay? And let's just call it to be some constant. Let's just call it this. Okay, all right, good. So now we're going to do this integration. Actually, I can use this board. Okay, so now let's look at Cmin to Cmax, alpha over C. So alpha over C is the cost of scrubbing. So it is Cmin to Cmax. The probability distribution function is actually a constant, 1 over Cmax minus Cmin. Right? D. D. Oh, sorry. Yeah. Right?
dc.
The probability of C, which is dp, right? No, sorry, this is P, this is P. Okay?
How do you know that? How did you know that the top of that graph is one?
Because the area has to be 1. Sorry? It's just an assumption. It's a bad assumption. But it's an only assumption which will make us solve the problem to some extent. Okay, so the next term is going to be linear. So it's beta C minus Cs. But this is going to be, the penalty is actually 0 if C is less than C star. So in this case, this lower integration will become C star. Right? Because if it is less than C star, the penalty is 0.
You mean CS?
Oh, C star.
The C minimum, yeah. If CS.
Oh yeah, C into C star.
Yeah, sorry, CS, yeah. So 2
I thought-
Cmax.
Isn't C max a star?
Sorry?
Isn't C max a star?
Cmax is the target concentration.
So it's
by
25.
optimization.
Oh no, never mind. C star. Oh, never mind. Never mind.
Okay. Cmax
Yeah,
is the
never
maximum
mind.
concentration, James. Okay.
Okay.
Times
Yeah.
times the probability, which is going to be 1 over Cmax min D C. Okay. How much time do we have left? 7 minutes. All right. So this is the most likely cost. Okay. So let's go through it again. The first term is the cost of scrubbing, right? So that term we're assuming is 1 over C, which actually makes sense. Our goal is to figure out the value that will minimize the cost, right? The value of C that will minimize the cost. And this penalty function, let's look at penalty because penalty is actually important. The penalty is 0. So let's say your C star. So this is CS, right? So this is actually the penalty function. But your C star, sorry? Ah, yeah, it could be linear. Yeah, it is linear. But your C star, which is what you're optimizing for, sorry?
It should start at 0 at CS and then go linear from there. There shouldn't be a step.
The penalty is 0 for C less than C star. Well, yeah, it should be.
Data times and
Yeah, based on this function, yeah, it is there. Okay, so the penalty looks like this, and the cost of separation looks like this. Right? So you can right away see that there has to be an optimum.
well, it doesn't go back up.
It goes to 0. Basically goes to 0 as C goes to infinity, right? So based on this, you can see that there has to be an optimum for some value of C, right? So we just have to do the integration, and after we do the integration, we differentiate with respect to C star, and we'll set it equal to 0.
You did everything you did to Cmax and then CS.
I think we'll continue it next time, yeah. Sorry, yeah.
How do we get to